What is up, math maniacs? Here we go. This is section 3.51, graphs and applications, functions. And we're going to take this over the course of a couple days. This is day 1. So anytime they ask for you to graph a function like this, where you can't just do y-intercept and slope over and rise over run, for example, it's a quadratic, it's a bit more complicated. I always think equation table graph. And so it looks like this. Equation table graph, equation table graph. It's just really helpful. You're given an equation, you can make the table, and then it produces the graph in that order. You can pause this and you can copy down the work. I do want you to see that I'm plugging in -3 squared, -3. If the x value is -3, it looks like this and produces this point. The value of the function is 24, so if the input is -3 and the output is 24, you can graph -3, 24, and there it is. You can do that the same thing for all of these points. And even you start to see a little bit of symmetry as well in the y values. 24 shows up not just this one time, but 2 times at the same height. This parabola, as we'll call it, is symmetric. And the symmetry is here. -2 shows up twice. -32 shows up twice down here. Equation table graph. Very important. Vertical line test. Now, here we've got a graph of some relation, and you can see that it kind of snakes around like this. And a function graphically will have all vertical lines cut the function 0 or 1 time. So if you are drawing vertical lines, then it looks like this. Vertical line, vertical line, vertical line, 1 time. It touches the function 1 time. However, you can draw a vertical line here and notice that it cuts the function 3 times. Now, if you can draw a line that cuts the function more than once, it's not a function. If you remember the call and response, when I say input, you say output 3. Now you could say 5, 2, or -1, and that's just it's not acceptable for functions. You've got to be able to have, every input has got to have exactly 1 output. When I say 3, you've got to say just 1 number. It's got to be very clear that there's exactly 1 number. But because there are 3 numbers here, this is not a function. And that's the vertical line test. It helps you rule out graphs of things that are not functions. So here, vertical line test. Is this a function? Let's find out. Vertical line. Yeah, it seems like every vertical line you could draw would only cut this at most 1 time. So yes, this is a function. Here, we've got a vertical line, and it cuts it 3 times. Therefore, it is not a function because of this. Right there. 1, 2, 3 times. So since it cuts the function more than once, it is not a function. Here, this is not a function because it cuts a vertical line can cut the graph into 2 places. Now, you might draw a vertical line over here, and that cuts it 0 times, and even you can draw a vertical line just as it touches that vertex. So it touches the graph 0 times, 1 time. It doesn't conclusively tell us at this point that it's not a function. Only once you go over here and see, yes, it touches it twice, then therefore it is not a function. I want you to do this one and tell me. And then here, you can see, yes, it is a function. Here you have to be really careful. I'm drawing vertical lines, and so far everything is good. Every vertical line touches the function 1 time, so therefore it is still a function. And here, if you draw a very careful vertical line, you'll notice that it touches it 1 time and does not touch it here. So this particular vertical line still only touches the graph once up at the top. Therefore, yes, it is a function. Had this been a filled in dot, then you would say no, because it touches the function twice. But it's not a filled in dot, so that's why it is a function. I'm going to teach you something new, something you probably not have ever seen before. This is what's called set notation and interval notation. So we've been using set notation that looks like this. If you want to talk about all of these numbers in between -4 and 5, and you don't want to actually include -4 and 5, then we know that you can use a set notation to look like this. All x such that -4 is less than x is less than 5. That's actually a lot of handwriting, and we're going to start, the closer you get to calculus, the more you'll start talking about intervals along the x-axis, for example, or along the y-axis. So the shorthand version of this is -4, 5. Now, you and I both know that -4, 5 could also mean -4, 1, 2, 3, 4, and then 1, 2, 3, 4, 5. This point right here, this is the point -4, 5. But that's not what we're talking about here. This is an interval, and this is a point. When we write -4, 5, it can represent all of these values along an axis. And you might be like, Mr. Bergman, how are we going to know whether or not we write this and it means a point, or if we write this and it means an interval? And the best answer I can give you is context. Just make sure that if they're talking about a point, then you know it's a point. If they're talking about an interval, then you can say this is going to be an interval. This shorthand is actually going to come into use the more we write intervals, the closer we get to calculus. So it's just a great shorthand to use. If you're looking at all the x values here on this second example, starting at 1.7 going up to infinity, for example, then here's how you would write it in set notation, and here's how you would write it in interval notation. Notice that now we have brackets. Brackets mean 1.7 is included. The boundary point is part of the interval that we want to express, and it goes all the way up to infinity. Infinities take parentheses here. So it goes like this, 1.7 up to infinity. If you want to talk about all the values between -5 and -2, but not including -5, then you make sure you put a parentheses here on the -5 and a brackets here on -2. So that way we talk about the values that you wanted to focus on. Of course, here, if you want to go from square root of 5, for example, all the way down to -infinity, then it gets expressed like this. And you can see -infinity, square root of 5, these both have parentheses. This has parentheses because infinity always takes parentheses, and this doesn't because we don't want to include the square root of 5 in our interval. One thing you'll notice about all these is that they always appear in order. So they have to be, you can't just say 5, -4. We have to make sure they're written numeric order. You'll notice that if you want to be using parentheses, that's very similar to an open interval, which is what we'll call this. This is an open interval. And an open dot you might have seen before, where you draw a circle like this. All of these things tie into the boundary value that's not being included. We don't want to include the square root of 5 here. We don't want to include the value of -5 here. We don't want to include the values of -4 and 5 in the example at the top. But here's a collection of ideas that all belong together. If you have a bracket, that's very similar to a closed interval and a closed dot. So here we want to include -2 in this interval, so we use brackets. And you've also seen people used closed dots. We call these closed intervals. This would be, for example, half closed and half open. Half open, half closed. So in general, you've got a kind of a ruled chart over here. This is interval types, notations, and graphs. This is what it looks like. These are all the different possibilities and what they could look like on a graph. Increasing, decreasing, constant functions. So here's what it means for a function to be increasing. By the way, these are all going to be open intervals. You'll notice that there are parentheses down here at the bottom. What it looks like to be increasing is you read it from left to right. Just we read text or reading a story. If you trace the function and you find yourself going up as you go from left to right, then it's called an increasing function. And here's the very top, it's -1, 5. This is increasing along the interval -infinity all the way up to -1. We talk about it in terms of its x values. It's decreasing from -1 to positive infinity. As you can see here, when we trace it with our fingers, it's going down. And increasing and decreasing functions are always answered in terms of x values and then open parentheses, because we can't really include this point as either increasing or decreasing. It's always talked about in terms of open functions, open intervals. Here, the function is decreasing until you get to this point and then increasing here. The way we can express that is it is decreasing from negative infinity all the way up to 2, and then increasing from 2 all the way up to positive infinity. Here, it's constant. This is a constant function because it's neither increasing nor decreasing. And so here, sometimes they'll have just some sort of wonky, undefined function. At least you don't have a formula, so you can, but you still have the graph and you can figure out which is increasing. It's increasing here only in the very middle. So we can say that it is increasing from 3 all the way up to 5, parentheses. It's decreasing from negative infinity all the way up to negative 1. It's also decreasing again from positive 5 as an x value to positive infinity. As you can see here, decreasing here and decreasing in the very first interval. And then yes, it is constant kind of in the middle. You can see here it's constant from negative 1 up to 3. These are all x values. Answer these increasing and decreasing questions in terms of x values and then open intervals. If you want to know how increasing, decreasing, and constant functions are explicitly defined, here it is. You can read it, and it's worthwhile to read. We're not going to use this particular definition very much. You'll use it a bit more in pre-calculus, and you'll use it a lot in calculus. But it's good for you to read, so take a moment to read it and see if you can understand it. But you can also just answer a lot of these very intuitively by looking at the graph. So we say that on an interval, for if a is less than b, then that means that f of a is less than f of b. And if you know that for any a, b, and I, then you can say it's increasing on I. In a very similar fashion, if you have an a value that is less than b, and it's on the interval I, and then you know for every f of a, it's going to be greater than f of b, then you know that it's going to be decreasing on this open interval I. And for all a and b in I, if f of a is going to be equal to f of b, then it's going to be constant on that interval. I just wanted to take a moment to say that Hartford is the capital of Connecticut, and I've only driven through it, but maybe you have more experience than I do in the capital of Connecticut, which is Hartford. I'd like you to begin assignment 3E1, copy the problem list, there's an M in the word problem, and then do the first problem. And once you've done that, I will see you in class.